Hello, everybody. My name is Lipson. I'm from Cornell University, and I'll be talking to you a little bit about this idea, which we call the matter compiler. An idea of moving from constraints, from needs, all the way down to something that can be made automatically. And it actually echoes some of the ideas we heard in the keynote this morning about how we can think about design in much less incremental ways, going all the way from need to a solution. So a recurring theme in the talks that we heard this afternoon was this idea that the people who are designing are not the typical engineers that used to do designs. We have increasingly designers that are not trained in engineering, designers that are motivated by different needs, that are enabled by new manufacturing technology that is becoming easier and lower cost, easier to use and lower cost to obtain. And how can we cater to these kinds of designers? So the main idea that I want to tell you about is how we can use this idea of 3D printing to enable new kinds of designers by offering new kinds of design tools that will allow them to take advantage. Now, we all are familiar with 3D printing and its ability to make arbitrarily complex shapes at press of a button. But one of the things that we're seeing that this is just the tip of the iceberg, and where this is really going also is into the ability to make parts that are made of multiple materials integrated in complex shapes and even functional behavior. And all of that presents very new opportunities for a new design space, new kinds of simulation and engineering tools, and new opportunities. So what's a matter compiler? A matter compiler is something that can go straight from a constraint all the way to a solution that takes advantage of whatever capabilities your manufacturing machinery can handle. Just like in software engineering, you go from a very high-level description of what you want the program to do. The compiler compiles it to the low-level machine code that's specific to your platform. So imagine yourself needing to design a bracket to hold up, let's say, a shelf at home. Somebody, again, that's not trained in engineering, doesn't know how to use CAD, can enter the load that the bracket needs to support, the volume it needs to sit in, the attachment points, and maybe the materials that are available, and the machine will take that and generate an optimal design that can be manufactured. So this is a kind of classic example. Here's a beam. I want it to be harnessed on the wall over here. It needs to carry a load. I let the machine optimize, and I get my solution. This is pretty much in real time, without the need to actually go through all the point and click and design and traditional design. But it can be more sophisticated than that. Let's say I have my design, and now I realize, wait a minute, I also want to leave room for a cable to go through the middle. So I put that constraint there, I hit enter, and I get a new design that respects my new constraints and is still optimal given what my particular platform can fabricate. So, of course, this can be done in 3D and so forth in lots of different ways. This is not real time, but it's getting there, and probably will be faster than that in the future. So this is kind of, this idea of topological optimization has been around for a long time, but often it has been hindered by the fact there was no way to manufacture these complex shapes. Well, now there is a way to do that, but the future is really going not just on topological optimization, but really combining multiple materials, optimizing also the microstructure, how lattices and how multiple materials interact, and even the behavior. And I want to show you a couple of small examples. Let's say you want to design a beam that flex, and you have a multi-material 3D printer. What we can do is we can say, okay, at the bottom there you see a couple of curves. These are specified by the designer. I want this beam to bend in a very particular way. I don't want it to bend in a classic way. I want it to bend in a straight line or in a circular line. I want to be able to prescribe a desired bending moment, bending shape. I hit enter, and the machine finds a particular combination of materials, a particular spatial arrangement of materials that gives me exactly that behavior. And again, I can do that without having to understand anything about how that works. We can go even deeper and think about how you combine materials at the microscale. And you can see here, combining two different materials in different ways gives me very different performances, and even auxetic materials and other materials that we have very little intuition about, but the machine can find these automatically. And lastly, we can even try to think about this in terms of behavior, moving to find combinations of material that give me a particular behavior. Here's an example of taking actuatable material, non-actuatable material, combining them together to make something that, let's say, can move. Here's an example of a solution like that, and here's the real thing moving. So this is, attempting to design robots in this way, but it gives you an idea. So the bottom line is, matter compilers will take your high-level ideas, constraints, needs, and compile them all the way down to material composition that can work on the particular platform and capabilities that you have. Thank you.